So it's a treat being here, and it's a treat also to speak to you guys, and hopefully this is a beginning of something even bigger. So we have like the visual intelligence program here in Tromsø in Norway. We have a similar thing going on in Denmark, the Pioneer Center that Robert just mentioned. It's just warming up, and I think there are already a lot of touch points. Robert is affiliated with the Pioneer Center, and there's a lot of ideas how we can get a more integrated effort in this important area for our society and for the world in general. So I hope that that the bits and pieces that I'm going to talk about here will be of interest, of course, specifically now, but also that maybe some of them could be sort of lead into other collaborations that we could imagine. So I'm not going to speak so much about specific applications. We do have specific applications in mind always when we do this research. So much of this is going to be so general that I hope that it can cover multiple dimensions of applications. So my own application area is in biomedicine and to some extent in media, digital media, sound and so on. And some of the examples will be motivated by that. So this work on supervised learning, or learning to label, of course, is core to, very important to machine learning. This may be the most sort of successful thing that we can do in machine learning, is to learn from data how to interpret data. So the typical thing is that we have an observation, some kind of event happening in the real world. We make an observation of it, and we like to understand what it is. So maybe link it to some known vocabulary of possibilities, or even to a knowledge graph or something more complicated structure. But that supervised learning traditionally has been done using labeled data, and it was the whole explosion of deep learning and so on happened to a large extent because we had these huge data sets of labeled data. That's not the typical situation, of course. The most typical situation is that we have a lot of data, we have a lot of observations, but relatively limited data or limited relevant data. And that's specifically the case for medicine, biomedicine, and specifically the case also for digital media, because both of them, yeah, this thing that is really expensive and hard often to need expert to label the data. Right? So that's why we for a long time have been interested in seeing, can we aid that supervised learning by also using the unlabeled data. And this, of course, is another explosion that is happening these years, is on self-supervised learning, as you all know, started maybe dramatically to improve natural language processing, but also important applications in both the visual and the auditory domain. So the auditory version of this has revolutionized speech recognition, for example. So just now we have a startup in Copenhagen, Alvenir, that is using Wave2Vec to dramatically improve Danish speech transcription. Because those structures are precisely like this, that it's pretty easy to get Danish speech, Danish text, but it's hard to get alignment. We had very little aligned data. Actually, the best aligned data we had came from Norway, from a Norwegian database that was public, with a bit of Danish in it. But now we have these tools that can help it a lot. So there's a lot of interest in this, and this means also there's been quite a bit of analysis. So in the old days, this was called semi-supervised learning, or I would say self-supervised learning is a specific instance of semi-supervised learning, the more general concept. And there are some theoretical results from semi-supervised learning that I want to bring out just to remind you that it's there, and also to bring it in contact with some of the new stuff that is happening. So I'm going to share with you some examples of from some very recent papers that have analyzed self-supervised learning, and also some of my own results that, like much of this theoretical work, one way or the other, have to study simple models like linear regression, for example. So some of the results that I'm going to show you of my own linear regression results. And the icon on the left, this little picture here I'm going to explain later, is the double descent phenomenon in linear regression. That if you haven't seen it before, you'll probably be surprised by it when you see it, that there are these linear regression can be so rich and show this phenomenon also. So the general idea is can be sketched like this, and specifically for self-supervised learning, that there are these two levels, that you first learn the data distribution, and then based on the data distribution, you learn structures, and those structures can then be related and help the supervised learning part, so you can get around with much less labeled data. So how little data can you get around to use? That depends a lot on the alignment between the two models, and this is much of what this is going to be about, is the alignment of the unsupervised and the supervised problems. I'm going to show you cases where this alignment is perfect in a way, and there you have exponential benefit of the labels. So error rates will go down exponentially as a function of the sample size. But of course, in most cases, it's much less effective than that, because we have misalignment of the two types of modeling. The what is called now pretext learning of the density function. So X is the observation, T is the target value, the label that we try to predict. And in supervised learning, the target is to say something about this conditional distribution. And the question is, how much benefit can we have if we know part or some of this the density function of the observations X. This book from about 15 years ago is still a very useful resource for much of this theoretical work also. So the unsupervised learning problem has many tools. So of course, much of what happens now is done by deep networks or complicated architectures. There are also simpler algorithms, things like PCA, for example, ICA, or the kernelized version of these, clustering and encoders and so on. And in general, when we do this modeling, it's typically in the setup where we could call it analysis by synthesis. So we try to analyze something by understanding how to create it, right? It's an important modus. And the density function is then parameterized by some structure that we can use later to understand the models. Similarly for the supervised learning, so once we have the density function, we can start to use that. There are many tools in the supervised learning toolbox, as you also know, but also many unsolved problems. And this integration of the two is one of them that we're interested in. So most of my early work on this was in something we call cognitive component analysis. So this was very much inspired by the independent component analysis tools. We try to understand in an event space, let's say in audio or in text or some specific domains. We have these events happening. So in text, it would be a document. In audio, it would be an utterance. Try to understand the latent structures and how well they were aligned with our cognitive efforts. Trying to say, if it's audio, for example, what is the concept of the speech, the transcription? So if you simply cluster speech, for example, how well are these clusters aligned with the structures that we know are in speech, like words or phonemes or sentences and so on? So that cognitive compatibility or cognitive alignment, this is what we dubbed as cognitive component analysis. And the idea is very simple. The idea is to compare the result of the unsupervised learning and corresponding supervised learning. So we have these events, cognitive events, and they can be pretty much anything, but the general thing is that there's a lot of possibilities. So there's 100,000s of words possible. So if we were looking at a representation of words, we need a very rich representation. And this means that most of this representation is going to be silent most of the time. So it's going to be a very sparse signal in a way, right? There'll be only a few things happening in a specific utterance. There'll be only a few words out of the many possible words present. In images, we can recognize a whole lot of objects, but there will only be a few of them present in a specific image, right? And in the text and so on, same thing. So we have this very rich event space X, and we describe it by some latent variables S, denoted here. And the probability of that, so that conditional probability, where we make inference about what is the latent variable of a specific, relevant for a specific event. Do that as the posterior distribution. So we have what we could call a generative model. So this is if I know what the latent variables are, what would I likely observe? And then we have a prior. So what are the most likely structures? Multiply the two and normalize it, you get the distribution they're interested in. So now the question is, did we solve the problem by that? Did we solve the labeling problem by that step? So if I have a reproducible way of guessing the structures, will that then be aligned with the labels? So is S equal to Y? That would be the best possible case in a way, right? So if I have clustering, let's say a clustering algorithm, I find that cluster, I say this utterance is assigned with this cluster. Does that also mean that I have recognized the words? That's the kind of question we're asking here, right? So if that happens, then we would say that the two are aligned. So we have this cognitive component analysis is active, right? So here are some examples. So this clip is from the first paper where we first defined this idea or sort of specified it. And then even more important is some work by Ling Feng, great PhD students who studied this at length and in several different media. So let me just to interpret sort of this evidence from different domains, let me just sort of give you an explanation of these three figures over here on the left side. So imagine that we make a very simple mock-up of this relation we're talking about. So I make a simple two-dimensional model of X. So I have just two variables that I measure. So I can make a scatter plot here. So every observation is a dot, right? That's one of these blue dots. So now let me think of the following generative model that I draw these physical effects. So there will be, in this case, also two of those. So there will be the S's, right? I draw them randomly and independently, and I draw them with different histograms. So in this figure, it's a normal histogram. So when I mix them, just observe the two variables into other variables, covariant structure of a normal variable, right? So now we have two independent variables. Now they're mixed into some covariant structure that we can identify just looking at that cloud there, right? Now, two other histograms would be a very sparse one and a very dense one. So if I had a very dense one, so let's say uniform distributions, for example, you get something like this. So if I had this mixing problem and my sources, the physical sources had a uniform, so they are sort of like equal probability on an interval, for example, I'll expect to see something like this. And then there's this structure up here where the two are very sparse. So this means that they have very long-tailed histograms. So think of something like a student T distribution, for example. So there's a very high probability that it's zero or nothing happens. And then there's this rare event where something happens that precisely happens to be this variable that I'm looking at, right? Then you get a histogram, a scatter plot like this. So what you see is that there are these two effects, and this is sort of the two stripes here, but there are also many places in this scatter plot that nothing happens. And that's simply reflecting that it's very unlikely that if they have rare events, both of them, it's very rare that they happen, both of them, right? That's sort of because they're independent, it's the squared probability, which is already low, right? So this scatter plot here is a sort of a signature we're looking for. And these lines or rays, they sort of indicate what the mixture is. So how much of one variable, S variable, is in this channel, how much is of X2 and X2 and so on. So here, this is what we're looking for, and here are some examples. So this is music, this is speech, and this is a social network. So you can see that very, very different signals, but they all share this structure to a very degree. So in the music case, the lines here, it's a very complicated picture. The lines are colored according to genre, to what type of music it is. Over here, you can't see it because the plot is so small, but these lines here are phonemes. So you have some sounds where we know what the phonemes are, and we can track for every dot here what phoneme is. So the phoneme is the sort of the unit of speech. In particular, the voiced phoneme, so the vocals, are very visible in this plot. And it's quite clear that these rays are rather linear. That's one thing we observe, but also that there's a lot of this sparsity phenomenon going on. So there's a lot of this intuition that at any given utterance, there's only a few of these vocals active, right? And then a little bit later, it's a different set, right? So it seems that this is a nice representation, and it's quite general also in the social networks models here. It's social relations that so it would be again something like genre in movies, for example. So this is the actor network that is formed by having many different actors, and we make a document as a movie which movie they participated in. And of course, actors, they come sort of in the genres also, just like the music does, right? Therefore, we can see the interaction patterns in this way. So this alignment seems to be really good for those media. So can we sort of say something more general about when we expect this self-supervised learning or semi-supervised learning to work, whether this cognitive component and picture is relevant. And unfortunately, it's not always the case. And this is what much of this theory is about, is to try to characterize these cases where it happens. And again, the intuition is super simple. So here is what I call the good, the bad, and the ugly cases of alignment. So the top one is where we have the exponential benefit of labels. And this is where there's a structure in the data. So here I just have one axis of X. And I've colored it so that the one class, the interesting. So that there are two classes. There's a gray and a white class. And you can see here that I have a lot of data here and I have a lot of data here. So these are like histograms, right? And the structure in the data is very well aligned with the labels. So if I only see just see that the X is the unlabeled data, and I found the two clusters, then I've almost solved the problem, right? So it's a little bit like what we just saw from the Feng's work, that once I find these stripes, then I just need to find out what they are. So here I basically need to find out which is gray and which is white. So if I just see the X's, I don't know that. I just know that there are a lot of X's here, a lot of X's here, but I don't know whether this is the pattern or this is the pattern, right? So you could say that as in this case, I maybe just need one sample. So if I get one sample, it's gray. I know that the other one is white, right? Now, and that's the good case. Now the bad case is where there's very little structure in the data, and the labels are kind of inventions of ours, right? That we have some cognitive activity going on that labels things as class A, B, and C, and so on, but it's not really related to the data, right? There must be something else. So I have sort of an example that I don't even know. No, you're going to post this on YouTube, so I don't know if I should say it. But it could be art, right? So there's the Italian painter that painted a white image, right? And it's worth $1 million. And of course, if I just post another blank image next to it, it's worth nothing, right? So it's only because of that the metadata that we know that this was the Italian painter that painted it, the white page picture. That's why it's worth a fortune, right? And that would be the case that like this, that there's no relation between the labels and what we're looking at. And there, I'm sure there are many other examples, but that's of course a case where we shouldn't expect too much from the unlabeled data. They're not going to help us a lot, right? But it can be even worse. So that's what I sort of indicated in the bottom plot, that there's a lot of structure in the data, but it's not related. It's actually misinforming us, right? So it's basically deceptive to get the structure. And there are examples of that also in the theory that we're looking at where this happens. Here's another old result. This is from the paper that, at least in some records, set the whole deep learning avalanche in motion, right? This is Hansen and Rosman Solutnikov's paper, was in Science in 2006, where they showed that by doing autoencoders representing data in low-dimensional manifolds, they could ease supervised learning of learning structure. And if you look at this picture here from the paper, you can see that there's a lot of things that resemble what we just looked at before, right? So they find exactly the same stripe or these rays that I talked about before. These are different data types, and you can see that in some of these structures are much sparser than others, but the general idea is the same, right? So here we would actually expect that we have a lot of benefit, and this is also what they find, that it helps a lot to do this kind of pre-processing to identify the structures before you do the classification. So now, once we have sort of absorbed this fact that it may be useful to find these statistical features just by looking at the distribution of the data without thinking too much about the label in the first place, then sort of an immediate thought is there must be something universal going on, because if I find the structure with different algorithms, the structure will determine what I find, right? So this means that if I run two versions of the autoencoder, for example, from two different initialization points, will be very different autoencoders. They'll have very different specific weights, but they should come up with the same explanations, right? Because it's the right structure, so to speak, that we are looking at. So this has been demonstrated also, and this is an example from supervised learning, but we could have done the same with the networks that Hansen created. And that is that there is a lot of universality in the features that we find because they're driven by data, right? They're not driven by the models. The models are able to represent these structures. That's the important thing. So here's some examples. It's a really interesting paper, again, also from 2016, where they showed that if you can solve the permutation problem in simple deep networks, then you can align the networks completely. So there's a very high degree of co-occurrence between the features in the two networks. That, of course, the details of it are very different, but the layers, so to speak, encode the same thing. And it's more so for the earlier parts of the network than for the later parts. So that's also an important thing that there seems to be more universality at the low-level features than at the high-level features in these models. So if they're universal, does that mean that when we solve this problem for a deep network, that we have solved it for the brain also? So how many of you see this as a movie? Yes, I know you're tricked, right? So as it says in the top, it's a misfire. So this is an image. There are no movies in my presentation here. So the thing that is moving here is in your brain. So this is the V4, one of the areas of your brain that process visual information early in the visual processing. It can detect motion, and it's never trained on pictures like this. So this means it has to find out whether what it looks at now is moving or not moving. And here it's tricked into assuming that it moves. So the brain will reconstruct motion even though it's not. So this is as you know, there's a lot of visual illusion and so on, and that's exactly that we have these features that are trained on large, useful sets of data, pictures in this case, but they're not fail-proof, right? I mean, if they meet something that they haven't seen before, something that is markedly out of distribution, you'll have to improvise, and it can sometimes mistake, right? And visual artists can make use of that to create displays like we're looking at here. So there are these, we call them in cognitive science, cognitive biases, that we misunderstand the data. And just like our models do that all the time, the brain does the same thing, right? It's if you go to Wikipedia and look at the list of cognitive biases, it's a mile-long list of places where the brain is doing the wrong thing, basically. Let's dig a little bit into the theory that we have for describing this learning from unlabeled data, supervised learning from unlabeled data. And the history goes back quite a bit, and it may be even longer than what I've found here. But here are some examples that I just want to bring out. So the first paper that I found sort of markedly describing precisely this phenomenon is Schotter's work from 65. So the idea is to train a model on an initial small set of labeled data, then classify a whole big set of unlabeled data, and then retrain the algorithm on that. And for that to work, you have to build a lot of constraints in. So today, this is not something that people do typically, but there are some conditions that are actually proven in this interesting paper also when that will make it work, that sort of self-training can work. They're very closely related paradigms. So this paper from 98, so Tom Mitchell's work on co-training is a very similar and related idea. So this is where you have two algorithms working typically on two different views. So the idea is to use this for multi-view data, multi-modal data, so say audio and visual signals, for example. Now you have a small labeled database of data that has been labeled for the two modalities, and you train a network on the audio and classify all the audio parts of the data. Now you use those labels to retrain the visual network, and that works. Co-training is super efficient. I have a small analysis of it in the linear case in a moment. But if you go to the original references and also later work, this has been analyzed in depth and shown the condition of when it works and when it works really well. So there are some conditional independence assumptions that will make it even work better, as we'll talk about also. Another important step forward in this theory is this work by David Miller and co-workers. So in this work, they take a Bayesian approach. So they say, okay, we have this unlabeled data, we have this labeled data. Let's just form one big likelihood function to train the conditional distribution. So there's two things to be sort of worried about now. One is that do the unlabeled data actually help the process? And the second thing, can they, because we typically have many more of them, can they dominate the likelihood function? Because the likelihood functions, if you, let's say we do log likelihoods, right, then it'll be additive. If we have more samples, there'll be more weight to that part of the likelihood function, right? So that's the problem. They attacked the second one. They attacked in this paper, and they show that if there's misalignment, so we are sort of somewhere between the good and the bad case. So we're not having perfect alignment, so we could just add the two sets. We should be a little bit careful. So they invented this discount parameter that say that we discount the unlabeled data with a certain amount, and then we have to tune that in, say, cross-validation or something as a kind of design parameter, right? Hyperparameter. So that's when the two processes are not completely aligned. So let me go a little bit deeper into, so I forgot to say that also here. So there's this paper, of course, very important paper from '95, and let me just talk a little bit more about what they do. So this is Castells and Kova's paper on the exponential value of labeled examples. Now we're in the good case. So we have two histograms of the two classes, and there's an overlap. That means that there's an error rate if we classify, right? So when I draw it before, the two clusters were sort of disjunct, meaning there was no overlap, so then we could solve it with just one sample. If we have an overlap, then the following can happen. So the labeled sample that I get, the first one, can be wrong, right? If there's an overlap, there's a small probability, let's call that R, that the label is wrong. And then if that happens rarely, of course, if the R is small, but the error is large, right? The error will basically be 1 minus R, because then I mistake the two labels rather than, yeah, it's clear. So if I get one sample, I get an error rate, and the error rate is sort of roughly 2R from this. Now, if I get 3 samples, then in order to mistake the two clusters from each other, two of the 3 have to be in error, right? And that, of course, happens with the R² probability, so much lower probability now. And this is the exponential decay of the error rate, that more and more, as I get larger samples, more and more have to be mistaken simultaneously, and that happens with a small sort of roughly R to that power, right? And therefore it's exponential power being the sample size now. So that's the argument. It's much more detailed, of course, in the paper, but the intuition is quite clear. So in the good case, this is fantastic. But now is that realistic also? And of course it's not. I mean, in most cases, there's some kind of misalignment between the two data sets, as we saw in the Miller paper. And this paper here is sort of leading into this discussion of what happens if we have if we're doing supervised learning with a small sample size. So let's imagine we have lots of unlabeled data, but only a small set of labeled data, and then things can start to go wrong, right? And now we are going to sort of dig a little bit into what can go wrong with these overparameterized cases that we can potentially help with the unlabeled data. So one thing that has been discussed a lot in the supervised learning case with too limited data, meaning that we have a massively overparameterized system, is what is called double descent. So the double descent phenomenon is that typically when we learn something like we have this exponential decay of the error rate, the more data we get, the better the models become, right? That's not the case always in these models that we're looking at now. And it's also not the case for linear regression, as I'll show in a second. If you do unregularized linear regression, you have the same problem. So here it's plotted in a way where we have the size of the model on the x-axis. What I'm going to show you in a second, I have data, the sample size on the x-axis, but it's very closely related phenomena. So you'd expect here that you have a kind of monotonic decrease here of the function, right? And it's probably easier to see over here. We have many traces where you have done training with a certain network size for a fixed number of iterations, and then you get curves like the ones you show here. So you have this hump here. So if you have models with roughly this size, then it's worse than having smaller models or bigger models, right? Which is sort of counterintuitive. Either it's overfitting or it's not. But here it seems that it can do both, right? So this is what I'm trying to understand in detail. So let's take a look at a very simple model that has a similar related phenomenon. So linear regression, and it's not only linear regression; it's maybe the simplest form of linear regression, where you have a target value, which is assumed to be sort of an inner product between a weight vector and observations of the x, and then you have additive noise, and the additive noise is simple also. So let's say it's normal distributed. So for this analysis, where I can do all the calculations, including computing the error analytically, I have to assume that the x is also normal distributed. So the observations that I have are also super simple, right? Normal distributions, and they have a specified covariance matrix. So right now, I don't assume that I know the covariance matrix. That's what I'm going to do later when I'm using the unlabeled data, right? But now I'm just looking at the semi-supervised, this double descent phenomenon. So X is a normal distribution zero mean with a covariance matrix, and the noise is zero mean with a variant. Now I have a number of observations. So we all know what the solution is, least squares regression. We get the solution is the solution to the normal equation. So we have the best possible weights in that sense, formed by having the input covariance matrix and inverting that and multiplying on the input-output covariance. That's the solution that we all learned in basic machine learning. Now, this is all fine if we have the well-posed case. So if the sample size is bigger than the dimension of the so here in this plot, the dimension is called lowercase d, and the sample size is n. So if n is bigger than d, then everything is fine. I can just invert this matrix here, no problems. If I'm in the over-parameterized case where the dimension of the space is bigger than n, then I have to decide how I want to solve the problem. And the solution I'm going to do here is with the so-called pseudo-inverse. I'm going to invert the matrix in the subspace that is defined by the data. That's maybe, again, the simplest thing that we can think of, right? So with this construction, it turns out that we can compute the generalization error. So if I had an infinite test set, I could compute the mean squared error. The mean in this case being on all combinations of x and y drawn from this the generative distribution up here. And I can also, and this is the more important thing, I can do the average on the data sets. So I can have a data set of a certain size, n, and I can think of all the possible data sets that I can create. That's an infinite list, of course, and I can do that average analytically. That's the beauty of this. So if I do that, I get this picture here. So we can solve it both for the well-posed case where n is big and n is small. So now I'm sorry, I have to switch the d here. Now is the dimension, the uppercase d. So in this plot, I have a double descent phenomenon. I have n on the x-axis and I have the error on the y-axis. I have two sets of points here. I have the thing that came out of the theoretical analysis that I'm going to speak briefly about in a second. And then I have an experiment also. That's the diamonds here. And you can see they put precisely on top. So there's no doubt we have the right thing here, right? So the result is the following, that if I have the usual case where n is bigger than the dimension, and it actually has to be bigger than d plus 1. In this case, I have a finite value of the generalization error, and it's given by this expression here. So it's proportional to the noise. And it involves the n, the sample size, and it involves the dimension of the space that we are modeling, but not the covariance matrix, and it doesn't involve the weight vector itself also. So it doesn't matter whether the sort of ground truth model that I generate the data with, what the direction of that weight vector is. So it's completely universal in that sense. So this is an old result. This part of the curve was I computed that in 93, and the other part of the curve was computed just a few years later in this paper here, which is about other really interesting and complicated dimensions to this, also with the noise and the uncertainty if you have a finite set and so on. And in the middle of that paper, there's a small paragraph saying we can actually compute that curve also here. We can compute that curve where it's in the overparameterized case. So that's where D is bigger than N, and in this case, N has to be smaller than D minus 1. So in this way, three values here, where N is equal to D, or D plus 1, or D minus 1, then the error is infinite. Now that's, I think to most will be a surprise, right? Because we had the solution like this. And if, let's say, we do the case where N is D plus 1, then everything is fine, right? And A is going to be regular. We can invert it. And for every sample that we draw, you'll get a finite solution, right? So how can the error become infinite in this case? It can, because the distribution of the error, so if you create a histogram of the error, so if you repeat the experiment many times and plot the histogram of the errors, you'll find out that the tail is very heavy. So there's a very high probability of getting a large error, and that error will increase. If you keep sampling, you'll see larger and larger errors, and the mean will grow to infinity. So even in something simple as linear regression, we have this really complicated, interesting phenomenon going on. So this is what we see here, and I can't plot the infinite ones, but I can plot the ones that are close by, and you can see that there's a lot of variation also, but the exact curve, of course, is going to be close to the mean in the experiment also if you repeat it many times as we do here. You can compute this curve here, as I said, analytically. You could also compute where the minimum is. So there's sort of a value where if you're in this regime here, then it actually hurts you to get more samples. So the error is going to be higher. So I think maybe if some of you are interested in how some of these specific mechanisms, that we can take an offline discussion later, because I think we understand in quite some detail why this happens. But it is kind of mysterious, and this is hopefully, I would say, informing us also about what we can expect in these much more complicated models with similar phenomena. Let me just say that the solution here in the overparameterized case has two components. You can see that this is very similar thing. So this peak here is in an interesting way symmetric. You just have to swap D and N, and that's a very simple symmetry in random matrices that give you that result. But it's also less. This solution here is also less universal. So it actually depends on the length of the weight vector, not the direction of it, doesn't matter, but the length matters. So that's a prediction also that we can go to deep networks with and see that if we generated deep networks with large and small weights, then we'll expect to see something like this, that there's a bias here, a kind of statistical bias term that depends on the length. And the reason is quite simple, that if you have a random, you have the direction of W is, let's say, in this direction, and now you have a random sample and it doesn't span the whole space, then there's a certain probability that it's going to hit that vector, right? There'll be a part of the projection would be outside the data set, and we lose that when we model. And that's the reason that it goes in here. And that part is bigger the bigger the vector is, or the longer it is. Now let's see how having unlabeled data can actually help us now in solving this problem in linear regression. So now I'm going to do another leap of modeling here, and that is to simply assume that I have infinite unlabeled data. So I have the small labeled set and non-infinite unlabeled data set. So with that data set, I can compute the covariance matrix of the inputs, the sigma matrix, right? And now instead of using the solution that I had before, I can just plug in sigma inverse instead. And because that's from an infinite data set, that's going to be the correct value, and it's also going to be regular, so I can invert it always. So I can for sure now sort of, I can say that there must be sort of a benefit, because this infinity cannot happen here, right? Because A is always finite, lowercase a. And sure enough, you can compute the whole thing again. The error can be computed, and if we look at the expression down here, we can see that it's there are terms that depend on N and D and so on, also dependency now on the covariance matrix and the weight vector. But the most important thing is that it's never infinite, right? There's no singularity in this expression. So this will be better than the linear regression results for at least for some combinations of N and D. Right? And here's an example. So here's the curve that we saw before, and here we can see how it fixes. So for a range of n's, then this is going to be better than the solution that we had before. So in this case, if we have a large unlabeled data set, then we can have a benefit in the linear regression case. For code training, you can do a kind of related analysis. I'm just going to show you the results. So this was this idea developed by Tom Mitchell and co-workers, where they have two views. So again, we can make a relatively simple model of the two views. So the two views are x1 and x2. And we're trying to predict y, and we have independence of everything here. So we'll assume that the noises are independent. And we'll assume that the noise in the views themselves are also unrelated. So there's a lesson here that we're going to return to in a second, and that is that if we have conditional independence, then this tends to help this addition of unlabeled data. And this is one example here. So again, if you run through the analysis, so you train the two modalities separately, and then you predict an unlabeled data set and use that for training. The data set that you train is for x2s with the model from x1 and so forth, labels from x1. Then you can compute the whole solution, and the regularized or the resulting solution looks like this. So we have the unregularized vector, and then you have this sort of ratio between two matrices, where one is the regularized covariance matrix. You can see that this is something that is smaller than 1, meaning that it's the regularizing. So it's kind of a shrinkage estimator that you get. So this is probably one of the mechanisms that you would expect for code training, is that this noise that you have in the two modalities separately would tend to regularize the overfit, right? So the critical assumption here is that we have independence of the terms here, so that the two noises and the two observation noises are independent. Let me just briefly talk a bit about, we should take a look at time also. How are we doing on time, Robert?
Yeah, so we're at 1:45. So yeah, maybe.
We just do a few comments here on a couple of new papers. So now fast forward to self-supervised learning. So I'm going to mention two papers. So one is this already now, I would say, a classic from 21. The title is Predicting What You Already Know Helps Probable Self-Supervised Learning. So they can continue this line of thought that I just mentioned, that if you have a conditional independence of the uncertainty in two views, so two parts of the signal, then you can achieve some downstream help in the modeling. So be more specific. So we have a signal X, and it could be two different modalities. It could also simply be two different segments of the same data. So maybe you have a time series. It could be that you're modeling a time window, and part of it you declare to be like in masked pre-training, for example, in language models or in speech. You predict one part of the signal from the rest of the signal, right? That's the substitution in this case. So basically, we're going to learn distributions like this. So conditional distribution of one part of the signal from the other, based on the other part of the signal. Now, let's just look at the case where we have conditional independence of the two. So this means that if I know what the label is, I'm looking at conditioning in one label set of the label, then I have conditional independence. So this relation holds that the joint probability is just the product of the two marginals. In this case, if we look at the thing that we are predicting here, so we can write it first by expanding it in y and summing. So this is the marginalization process. And then we so this is the joint distribution. I just factor it out as a conditional distribution and a marginal. Now, if I have the conditional independence, then I can delete the x2 here, right? And this means that this prediction problem that I'm creating in the self-supervised case runs through y. So y is a bridge between the two variables. And this means that if I can predict x1 from x2, it goes through y. And that's why it's going to help us later when I'm going to use that for predicting y, right? So that statement is, of course, a strong one, and it doesn't hold it in typical cases. But in the paper, they then go on to say if it holds approximately, will it then help? And it, of course, depending on how well it holds up. So what can go wrong in this argument here? It can be that there are other physical phenomena that link the two modalities. So that what we could think of as confounders. And I think that's one of the big sort of open problems at the moment in this theoretical work, is to specify the confounders that could link the two things that you predict. So could there be other bridges between x1 and x2 than y? Could there be other latent variables, so to speak, right? Then we have to condition on those guys also in order for this to hold. There's another even more recent piece of work that is from this year. The parts that I've clipped here is from a paper that came out just a few months ago. So here the idea is to characterize the density functions that you learn, so the manifolds that you learn from the self-supervised or the learning the density model. If you can characterize that structure in terms of things that you have control over. So one case that they study is data augmentation. So imagine that you have a data point and now you present the network for multiple versions of this with different augmentations. So in this case, rotations. And what we are trying to find out now is how do these embeddings, the latent variables, how do they form a structure? So let's imagine that you have a manifold, in this case a dog, right? The dog is on a manifold. Now we look at the different versions of this particular dog. What is the structure that it creates? Is it low dimensional? Is it high dimensional? They create a number of features, and they show that these features can be used to predict whether it's going to help us downstream or not. And the important distinction here, and this is what quite a few papers is also working with at the moment, is to, if we think about data augmentation as, let's say, rotation, then the typical thing that we'll do in order to, I hope that we'll get from the showing the rotated images and training on the rotated images, is that we become invariant to rotation, right? We say that this dog and the rotated version of the dog is still a dog, right? And therefore, we would like the network to predict dog no matter what the rotation is. And if that's the case, then we'll imagine that this is a very small set that because when they propagate the rotated dogs through the network, then in this representation, it would basically forget about the rotation, right? It'll just bring it to some common point, which is the notion of the dog, right? So in this case, we would think that the mechanism we have created would generate invariant representations. Now, it could be that our task downstream was to recognize the rotation angle of the dog, right? Then this would be a disaster because we would have basically killed the signal we're looking for. So in this case, we would have hoped that we get here a rich representation in the manifold. We would hope that we have something that represents the rotation angle. And this means that it's what we call an equivariant representation, right? So basically, by these different measures that they create, they parameterize the space of invariance to equivariance. And then we simply have to understand better the downstream task, whether they're going to use one or the other of those two, plus other similar features. This idea has been also represented in other works in different ways. So I think it's maybe really clear in this particular paper. There's a paper by Eriksen here also and others where they have a very similar idea. So they have the same observation, I would say, in many ways, not parameterized in the same way, but the same observation. But they simply suggest that we concatenate these representations. So we learn with equivariant, invariant, and different intermediate versions of that. And then we let the downstream task decide for itself which part of it wants to use. So that's, of course, a very, very related idea. So we already saw that there are go theorems for semi-supervised or learning with unlabeled data, like the good cases that we have looked at with exponential benefit. There are also no-go. We saw that Miller and also the cases we just looked at, that there could be no-go versions of it, that we learn invariance, but we need equivariance, for example. It turns out that there's other sort of descriptors that we can use for describing the learning problem that also leads up to go and no-go theorems. So one particular, this is a case that I studied myself. I don't have time to go into detail with it. I'll just show you the results. So this is a very general way of thinking about machine learning, where you learn predictive distribution. So this is a Bayesian way of studying machine learning. And there we can come to a conclusion on the optimal predictive distribution. So if I'm sort of looking through all possible ways of doing supervised learning. So this would all these conditional distribution where I condition on the data set, also learning from data. The best possible conditional distribution is Bayesian averaging, and it's actually what is called transactive Bayesian averaging. So we have to use the X in the posterior distribution. Now, in that case, I can ask if I have labeled and unlabeled data, should I then use all the unlabeled data also in my data set here? And it turns out that you should. If so, this is a complicated expression, but the message is very simple. You should if this is the case. So now let's look at the through distribution that we think is generating the data. So it has in the conditional distribution parameters θ1 and θ2. In the density function that generates the input data, we have θ2 and θ3. If there are some parameters that sort of cut across the two distributions, in that case, we should use all the labeled data, all the unlabeled data for the modeling. If this set here is empty, so if you have a modeling case where there's basically no learning from the input distribution to the conditional input-output distribution, then it's almost sort of intuitively evident that you shouldn't use the unlabeled data. You would say maybe in the best case you have no benefit from, but you can also prove that. It's very easy to see that in this very general picture that in this case there's no benefit from the unlabeled data. So you shouldn't use them; they can only hurt you. That leads me to the unsolved problems that I wanted to mention. And do we have time for it? We should probably.
Yeah, maybe 2 minutes.
Maybe 2 minutes. Okay, so let's just think about cases where we have sort of this situation where we have a link between the two distributions. So we think that there's a potential benefit of the unlabeled data. Then we can discuss sort of which distributional families will allow us to get a benefit. And there are some results. So this old paper by Marty and Kent is an example where they show that in some exponential families, we can prove that this is the case. We can prove that there is this relation that the input distribution and the input-output distribution have parameters that are joined. And we can even show that the exponential families that they have sort of this exact relation that it becomes a Go version. Now, again, it's interesting to look at this for linear models, and I did that. So here's a result for predicting the covariance matrix using estimating the covariance matrix using linear regression. So I predict x1 from x2 and x2 from x1 in the same setting as we talked about before. And it turns out that then the picture again is really complicated. So this is what I'm showing here. So we have the well-posed case out here. Then you have this exponential family is then realized. But if you're in the overparameterized case, then many things can happen. Sometimes it's better to do unsupervised learning to learn the covariance matrix. Other times it's the pretext learning can improve. And there are these spikes here. So there are spikes like the ones we talked about before that derive from the case where you hit precisely a dimensionality and the sample size. And that depends on how you regularize, of course. So super interesting unsolved problems. And I think with this, let me not run too much over time. So thank you, Robert.